Sorry, just getting familiar with this Blackboard. Normally don't use Blackboard to share, but welcome. Again, my name is Ruben Carrizales, and normally you guys are used to having Mr. Isasi do this lecture. He's in a conference right now, so I will do my best to go over his material for all of you. So, so he uses a PowerPoint presentation to do his presentations. So I can see the chat. So if you have a question for me, please, by all means, just unmute yourself and ask. Okay, and I will stop or go back with any questions you may have. So without further ado, let's go ahead and get started. So for today's session, he has us covering sets, probabilities, permutations, and combinations. So these are all the topics that we're going to cover under this title, and these are some of the key points that we will go through. So I guess let's start first with what a definition of a set is. A set is a well-defined collection of objects. Okay, so he has examples of these. An example of a well-defined collection of objects could be all the students in his math class, right? In his 1324 class, or the letters in the alphabet, right? These are a well-defined collection set. So um, if I were to say, I want to find a collection of young adults, well, this is not a well-defined set. I mean, what, you know, young adults would be a better, or to better define it, would be like young adults between the ages of 12 and 13, something like that. But just young adults is too broad, is not well defined. So, oh, then he has an example of how to better well define it. We want to look at young adults between the ages of 18 and 29. This constitutes a set. Okay. Now, um, we are going to be giving names to sets, and um, the most popular names that we give names is just the letters of the alphabets, which is A, B, C, and we always capitalize, just like how your name is capitalized. We capitalize these. We normally don't use lower cases to name sets. We always use the capital letters. Okay. All right. So each object in a set is called a member or an element. So if I were to go back to the collection of young adults between ages 18 and 29, all the young adults that are within this age group, these are called the members or the elements in this set. Okay, so it's everything that's part of the set. So um, when we are using objects, okay, to indicate that we're talking about a set of objects, we use brackets, these curly brackets, to enclose the objects, okay, in a set. So, for example, have this set A. The name of the set is capital letter A, and the elements or members in the set are 3, 4, and 5. Okay. Now, um, so we say the set A consists of elements 3, 4, and 5. Okay. Now, this symbol, this is a Greek symbol E, okay, or it looks like an E, right? It's for an element in the set. Okay. So when we use this element, or the inverse of this is a little line through the E, a slash through the E, and this means not an element in the set. All right. So for instance, I go back to my set A, and if I want to do the um, set notation, right? We have 3 is an element of A, or 3 is an element of set 3, 4, 5. And that's how we would use this element. E is an element in the set. So these are how we would read it. 3 is an element in set A, or 3 is an element of the set containing 3, 4, and 5. Okay. Now, what about this one? Since we have the E symbol, the Greek E symbol, as a not, so we say 2 is not an element of set A, or 2 is not an element that is 3, 4, or 5, right? So this is how we would use these notations, right? So sets and definitions and examples. So let's first talk about the empty set. An empty set is a set with no elements, okay? So the symbol that we're going to use for an empty set is a little zero with a slash through it, or just the brackets but nothing in there, okay? So it's very important that if you're going to use the empty bracket symbol, you don't put anything in there, because if I would put empty brackets and I put the number 0 in there, that's not empty. That means that that set has one element, which is 0. It's in the number 0. So do not put anything. If you're talking about the empty set, it's either just a 0 with a slash or just the brackets with nothing inside. So please be careful with that. It's called the empty set. Okay. An equal set is any set that contains exactly the same elements, okay? And we'll see some examples of these. So he has it here. So these are equal sets. The order does not matter as long as the elements inside the set are the same. So for instance, the first set is 3, 4, 5. That's equal to 5, 4, 3, because both sets have the same number of elements and the exact same ones, 5, 4, 3. Again, the order does not matter. These are all equal because they all have 3, 4, 5 or 5, 4, 3. Okay, so this is what makes sets equal, that they have the exact number of elements in each set. All right, so here, sometimes we like to use set builder notation to also describe sets. So there's several ways to um, listing sets. The first examples that we went over, but we didn't mention, or he didn't mention, the notation on that is just the list method. You know, they're just listed 4, 3, 5. Okay, but we also have something called set builder notation. And let me give you an example of how we read set builder notation. So here we have a set, and it's in set builder notation. And I believe he has a representation of what this means. So the first thing that you'll see in the set builder notation after the squiggly bracket is the name of the set. So this set is set X, okay? And um, and it's talking about all the elements in this set. Okay, so this little line, it's called a pipe. It stands for such that. So X, all the elements of X, such that, and then what we're looking at. X has a property of P. So these are what we're looking at. So let's look at examples of a set builder notation and what they stand for. So the first one says um, X such that X is a natural number more than 5 and less than 8. Okay, so here the set that this is describing is just 6 and 7. X is a natural number, so we're looking at the natural numbers. More than 5, so more than 5, if that was just that alone, it would be 6, 7, 8, 9, 10, 11, you know, and so on. But we also have another condition that says less than 8. So less than 8 would be 7, 6, 5, 4, 3, 2, 1. But we only want to look at the numbers between 5 and 8, so it would be just 6 and 7. So this is how it's nice to use English words in our set builder notation to describe also the sets, right? So let's look at B. X such that X is an integer and um, X is between -3 and 1. Okay, so here, when we're talking about the integers, we're looking at both negative and positive numbers. But we also have another condition. We want to look at only the numbers that are between -3. And let's look at this interval notation. We want x to be greater than -3, and we also want x to be less than or equal to 1. Okay, so the numbers greater than -3 are going to be -2, 1, 0, and on. And the numbers less than or equal to 1 will be 1, 0, and so on. So the only numbers in our set here are -2, -1, 0, and 1. Okay, so set builder notation, you'll be asked to give sets in this form. Okay, all right, so you need to know. So he puts it on there. You'll get tested on this. All right, so he also has a review when we're dealing with numbers. Whole numbers are the 0, 1, 2, 3. The counting numbers um, are 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 similar, except again, you don't have any decimals, and then the natural numbers are counting numbers. Yes, so again, need to know. So let's look at sets here. Sets state whether the statement is true or false. So again, if we recall, that little Greek symbol E, or looking E, says that 3 is an element of this set. Um, and the set here is described as 2, 5, 7, 9, 10. Is 3 a number in this set? No, right? So this statement is false. What about 2? 2 is an element of this set, which is 2, 5, 7, 9, 10. Oh, yeah. 2 is on that set, so this is a true statement, right? Oops. So 2 is an element in the set. All right. 3. The way we read that is 6 is not an element of 1, 3, 5, 7, 9. And that it would be true, right? 6 is not in that set, so that is a true statement. All right. Number 4. 4 is not an element of 2, 4, 6, 8. Oh, this is a false statement because 4 is in that set, so that is false. All right. How about 5? Oh, it's trying to see if these two sets are equal. So again, for two sets to be equal, they have to have the exact same elements in both. So for the first one, I have the elements 1, 2, 3, 4. The other one, oh, I have the same. They're out of order, but they're the exact same ones. 1, 2, 3, 4. So this is a true statement. All right, how about 6? We have A, B, C, and then we have A, B, C, D. What do you guys think? No, right? This is a false statement. For two statements to be equal, I have to have the same number and the same elements inside. So since the other set has one more additional element, they're not equal, okay? It's like saying 5 is equal to 6. No, right? 6 has one more number or one more value than 5, so they're not equal. They have to be equal, right? Um, how about 7? The first one is in just in English um, words. All the whole numbers that are greater than 5 and less than 9. So whole numbers greater than 5 are 6, 7, and 8. But and because we want them also less than 9, so this would be um, a true statement, right? How about number 8? All natural numbers not greater than 4. Okay, so again, this would be a false statement. Why? Because our natural numbers or counting numbers do not include 0, right? 9. Oh, this one on the left one is in set builder notation. So we have x such that x is an even integer. All right, so we're looking at even numbers, but then we have another condition. We also want x to be between 5 and 19. So we're going to only look at the numbers between, even numbers between 5 and 19, which would be 6, 8, 10, 12, 14, 16, and 18. So do we have that going on here? 6, 8, 10, 12, 14, 16. Yes, so that one. Oh, am I missing one? Did I miss? Oh, I'm missing 18. Excuse me. I didn't have 18, so they're not equal. All right, number 10. X such that X is a vowel. Oh, the vowels are A, E, I, O, U. Ah, this one's a true statement, right? Excellent. All right. Now let's look into subsets and proper sets. Okay, so we're getting ready to be able to go into drawing these sets visually. That's called Venn diagrams. But let's get some terminology first, okay? So a universal set is a set that contains all the objects being discussed. Like I like to say, it's the universe. Everything that's in my universe, that's what's going to be inside here, okay? So everything. Um, Subsets and proper sets. So let's look at the definitions here. A set A is a subset of set B, and we write subsets as with this little C, elongated C with a line underneath. Um, and what this is saying is that every element of A is also an element of B. That's what a subset is, right? That all of the elements in A are also in B. Okay. Again, if you have questions, please just unmute yourself, okay? Because I can't see the chat. I heard a ding, but I didn't. I can't see it. So if you have questions, please stop me or let me know. Okay?
It's just the passport code, Mr. Curzon.
Oh, okay. Thank you. Um, all right. So proper sets. A proper set. The way we read this is A is a proper set of B if every element in A is an element of B, but B contains at least one element that is not in a member of A. Okay, this is what's called a proper set. And then the last tier that we have is when A contains an element that is not in B, then A is not a subset of B. Okay, and then again, the not is by drawing a line between the symbol for subset. Okay, all right, so some more definitions or terminology. Okay, for any set A, so what this first one says is that the empty set, okay, is a proper subset of A, and the empty set is also a subset of A, and A is a subset of itself, okay, because all of the elements in A are in itself, right? So that's what those three mean. That the empty set is a proper subset of A, the empty set is also a subset of A, and A is a subset of A, okay? All right, so let's look at some examples using this terminology. Oops. Um, so these are my examples. These are my example sets. Set A is ABC, set B is ABCD, and set C is CAB. All right, so, oh, there's no animation on this. Okay, so the first one, A is a subset of B. So what we're reading this is that every element in A is also in B. Okay, B. Oh, that's the symbol for proper subset. So the way we read that is every element in A is an element of B, but B contains at least one element not in A. Okay. Um, C. C, the way we read that is B is not a proper subset of A. So that means that every element of B is not in A. Okay. D. A is a subset of C. So the way we read that is every element in A is also in C. Okay. E. That's the not. So A is not a proper subset of C. So the way we read that is A is not a proper subset of C because A is not equal to C. And then the last one, the empty set. The empty set is a proper subset of A. Yes? All right. So let's look at some some actual work. Let's get these sets. Let A equals -4, 0, 4. Set B is -3, -2, -1, 0, 1, 2, 3. C is -4, -1, 0, 4. D is 0. Okay, that's not means empty. There's one element in there. E also has one element, -4. So then the U here. The U, as before, represents our universe. Okay, it's all of our elements in our universe. So that U, or that symbol that looks like a big U, is giving me all the elements that are included in my universe, which is from -4 to +4. Okay, so the assignment says insert a proper subset or not a subset to make the given statements true. Okay, so let's look at the 11 here. A and U. Okay, so A is just -404 and U is my universe. So to make this one a true statement, A is a proper subset of U. And why is it proper and not a subset? Because U has other elements that are not in A, right? So this makes my statement true. All right, how about 12? E. E is just one element, -4, and A is -404. So again, this is the same thing. The reason why this is a proper subset because A contains more elements than what E contains. Okay, how about 13? AE. Okay, so AE is not a subset of E, right? And for this reason is because the elements 0, 4 are not in E. Okay. How about 14? B and C. So B and C again is not a subset, and the reason for that because -3, -2, 1, 2, 3 are not in C, right? How about 15? The empty set and A. Oh, this one is a proper subset, right? Because the empty set has nothing the and every empty set is a proper subset of a set, right? It's part of our definition. So how about 16? 0, 1, and D. So this one is not a subset, right? And why is it not a subset? Because element 1 is not in D, right? All right. Oops. D and 0, 1. So D is a proper subset of 0, 1 because there's at least one more element in 0, 1 than D. D only had the 0, right? How about DB? DB is a proper subset because D contains at least one more element. Okay, and the last one also. A is a proper subset of C because C contains at least one element not in A. All right. Again, hopefully I'm not going too fast. Okay, if you have any questions, please let me know. Okay. All right. How about dealing with subsets? List all the possible subsets for each other giving sets. So A, 4 and 6. So let's go through them. Okay, all the subsets means just it could be just one or all of the elements that are in my main subset. So again, Mr. Sassi here wrote us a definition. A set A is a subset of set B, provided that every element in A is also an element in B. So for the solution of A, okay, we have the empty set, right? That is a subset of 4, 6. We have 4, we have 6, and we also have 4 and 6. So these are all the subsets of 4 and 6. The empty set, 4 by itself, 6 by itself, or 4 and 6. Okay, easy stuff, I hope. All right, how about B? Let's do B. So the solution for ABC, again, we always have the empty set as part of the set. Okay, we have A by itself, B by itself, C by itself, or we can have AB by itself, or we can have AC by itself, or BC by itself, or finally ABC. So the subsets of ABC are the empty set A, B, C, A, B, A, C, B, C, and A, B, C. Yes? All right. So if you're asked, maybe in a test or homework, if you asked to find how many subsets does a particular set contain, you can use this definition. A set of n-distinct elements has 2 to the n subsets. So let's see, does he, so we have some examples here, okay? Um, so for number 20, find the number of subsets in the given set. So 20 has one element, 3, right? So how many subsets are we going to have? Well, 2 to the 1. So 2 to the 1 is 2. So we have two subsets. What are those? It was the empty set and just the number 3, right? You see the 2, right? How about 21? How many elements do we have there? We have 3, right? We have the red, white, and blue. So 2 to the third power, that is 8, right? 2 times 2 is 4. 4 times 2 is 8. So we have 8 subsets, okay? How about 22? That's in set builder notation. We have x such that x is a whole number less than 5, right? So the numbers less than 5 are 4, 3, 2, 1, 0. How many elements are there? Those are 5. So 2 to the 5 is 32 subsets. Yes? Easy, right? So if we look at the ones before we had, like how many subsets would 4, 6 have? Well, those are two elements, so that's 2 to the second power, so that's 4, right? And you see 4 there. The ABC, how many elements we have there is 3, so that would have been 2 to the third power, right? So that would have been 16, right? 2 times 2 is 4, 4 times 2 is 8. No, excuse me, 8. Not 16, going one too many. So we have 8 elements there, right? All right, operations on sets. Given a set A and a universal set U, the set of all elements of U that do not belong to A is called the complement. And the way we write complement is by a little hyphen. So for instance, the complement of A is written as A hyphen, right? Or read as A prime or not A. It's the complement. Okay. So any of those um, is how we interpret or read those. So let's look at an example. Let's have my universe U. Okay, these are all the elements that are part of my world. And we have a subset A, okay, which is just 1, 2, 3, 4, or set A, right? So now what I'm going to introduce or how we're going to write this is in Venn diagram notation. It's drawing pictures. Okay. So first, what you need to know is that when we are describing our universe is always encapsulated in a big rectangular box. This big rectangular box is now going to represent my universe. Okay. And we label it U. Okay. Now that U can be anywhere. Some books put it on the top corner. Some put it inside the little square on the left-hand corner. Some on the right. Some on the lower left. Some on the lower right. It doesn't matter. Okay, as long as you have it on there. Okay. Um, Objects in my Venn diagram or sets are described as circles. So this circle here is going to be labeled A. Okay, this is my circle A, which is my set. Now, what normally I don't do the A inside the circle. I put the A right on top of the circle because it can be confusing because the elements inside my set are just the numbers 1, 2, 3. But for right now, I think he put them like this just to explain what is A and the complement of A. So A is my circle, right? Is everything inside my circle. So the complement would be everything that's outside the circle. And we noted that as A prime or not A. Yes? That's why he did that. All right. So let's find not A. So if I wanted to find not A, um, let's do this. So and this is my universe, and I write what A is. Okay, A is one. Where's my A? 1, 2, 3, 4. 2, 3, 4. This is what's in my A. So not in A is everything that's outside, which is part of my universe, and all these numbers would be outside. The 5, 6, 7, 8, 9, 10, 11, 12. He has good, cool animations, right? So if you see here, when we use Venn diagram, it's very easy to see the answers of what not A is. We just look at and write all the numbers that are outside my circle. So all the numbers that are outside my circle are those 5, 6, 7, 8, 9, 10, 11, 12. So that's why we love Venn diagrams, because Venn diagrams is a visual way of doing sets. Okay. All right. So another definition to get us familiar with Venn diagrams is the intersection. of two sets. So the definition here, if we are given two sets A and B, the sets elements that belong to both sets, and we say that A and B, this is called an intersection. Okay, and the way we write intersection, instead of the big U, we flip it because U means the union, it's everything, but the opposite, that means intersection, like an upside down U. So we read that as elements belonging to both sets, A intersection B. So again, is what they have in common. So let's look at another example. Let's have my universe, and I have a set A, which is 1, 2, 3, 4, and I have my set B, 2, 4, 6, 8. So let's go ahead and first do it visually, right? What intersection means is values that they have in common. So in set A, do you see that we have they both share a 2 and they both share a 4. Those are the only two elements that these two sets share, the 2 and the 4. So the intersection of A and B would be just these two values, 2 and 4. So if we were to use our Venn diagram, this is how it would look like. Okay, my universe would be the square box, but now I have two sets, so I have two circles. One is A, the other one is B. Again, I like to put them on top of the circles, not inside. And then the elements of A, um, or the intersection would be this is where the intersection B is, where the overlap. I like to tell students, hey, it's like the MasterCard symbol, right? That's what's inside. That's the intersection, A intersection B. So let's go ahead and put our values. This is our universe. Again, the intersection is the values that they share, which is just a 2, 4. And A has the values 1, 2, 3, 4, right? But you see that where we put them perfectly so they can align with my other set. My other set is B, and the elements are 2, 4 that are already there, and 6, 8. They're not included inside this little overlapping part, right? So again, if someone would show me just the Venn diagram without even thinking, I would say, oh, okay. The values that are shared by A and B are those that are in that overlapping section, which is 2, 4, right? So again, I love Venn diagrams because I'm a visual learner. I like to see things. All right, so again, if I were to finish my Venn diagram, the universe outside these two sets is everything that's not either part of A or part of B. So the 5, the 7, the 9, the 10, 11, 12, oops, all go outside the circles again. And it doesn't matter where you put them as long as they're inside this rectangular box, inside my universe, okay? And if you see, all of the numbers that are in my universe are inside this square, and the sets A and B have their own values inside. Yes? All right. So let's talk about disjoint sets. So the definition, um, for any set A and C, if A and C are disjoint sets, that means that the intersection of A and C is the empty set. So again, in simple words, disjoint sets means that we have sets that have nothing in common. They don't share and they don't overlap. And that's the best picture, that they don't overlap. That's what disjoint means, that these two sets do not touch or overlap, right? So let's look at this example. We have our universe, we have a set A, we have a set B, and we have a set C. So let's do find A intersection C. So that what that means is what is in common in both sets A and C. So if we look at both A and C, A has 1, 2, 3, 4, C has 5, 7, 9, 11. They have nothing in common, right? So the answer would be the empty set. So this would be considered, A and C would be considered disjoint because they don't have anything in common. All right. And if we were to show this on our Venn diagram, this is what it would look like. Okay. This is my set A. This is my set C. Um, and if I put the values that I have for set A and set C, A is 1, 2, 3, 4. Set C is 5, 6, or 5, 7, 9, 11. 5, 7, 9, 11. You see they don't overlap. There are two different sets that have nothing in common. So this is disjoint. Again, so since they don't share anything, my answer is the empty set, right? All right, let's look at another example. Let's finish it off. Let's put in all our values that are in the universe. So everything that's in our universe that's not part of these sets, go outside these circles. And again, it doesn't matter where you put them, okay? All right, so how about the or? We saw the and is the intersection, right? At A and B, I want to look at the values of A and B. Now in English, the or refers to union. So the formal definition of union is two sets, A and B, that the set of elements belonging to set A or B is called the union of the two sets, written as A union B. Now this one is union, right? It's um, this format. So what the way I like to think of union is I want to look at everything that that is that results of putting two things together, right? But you got to be careful. We don't count duplicates, okay? All right, so here in red, it says list of all of the elements that are both sets, but do not repeat again. No duplicates. That's what I meant. So I'm glad he's very detailed. All right, so let's do this example. Let the universe set U be this, and set A be 1, 2, 3, 4. Set B be 2, 4, 6, 8. So let's see what he has us do. Find A union B. So what that means is I want to have all the values that are in A or B, okay, no duplicates. So here we start with A. A is 1, 2, 3, 4. And B, well, I already have 2, so I don't have to write it again. 3 is not in B, but 4 is already there. But I do not have 6 and 8. So those will be the 2 that are left for my union, the 6 and the 8. So that's what A union B would be. 1, 2, 3, 4, 6, and 8. It's all of the ones in A and all of the ones in B, but not doing duplicates, right? Because it's the same number. What? Don't have to write it twice. All right, so if I were to use Venn diagram to give this answer, okay, again, I have two sets, A and B. This would be A and this would be B. Um, and the union would be everything that's in both of these, A and B. So look, when we write this with the numbers, our set A has the 1, 2, 3, and 4. My set B would have the 2, the 4, but also has the 6 and the 8, right? So the 2 and the 4 is my intersection, but the union is all of them, right? So it would be 1, 2, 3, 4, 6, and 8. You don't see any doubles, twos or double fours when I have it visually in my Venn diagram. All right. So to finish it off, all the other elements that belong in my universe go outside these objects or these circles, right? They're just anywhere. Doesn't matter where. All right. Operations of sets. So let's do some terminology. Let A and B be any sets with a universe signifying our universe set. Then the complement of A is written by A prime. Okay. So this is, I can write this also as a set builder notation. Okay. So A prime can be written as X such that X is not an element in A and X is an element in the universe. Okay. So that's how we read, or that's how we can use set builder notation to also write our complements. And this is what a picture would look like. Okay. A is just my set in the circle. Not A is everything outside the circle that belongs in my universe. Okay. How about the intersection of A and B is, okay, in set builder notation, we read this as X such that X is an element of A and X is an element of B, right? So the way we look at that in our Venn diagram is the region where they overlap, that shaded region. again, my MasterCard. All right, how about the union? A union B. Instead builder notation, we write this as X such that X is an element of A or X is an element of B or both, right? So this is what the union means. All of A and all of B, all of the elements without including duplicates. All right, so let's do some exercises. Let my union be that, and then I have my sets X, Y, Z. We change, right? Again, these aren't just names, and since they're names, we do capital letters. So we're not using A, B, C. We're using X, Y, Z now. All right, so let's look at 23. And the assignment is telling us list the members of each of the given sets using braces. Okay, so the first one, 23, is that's red. Set X with its intersection of Y, right? So we are only looking at the values that they share, only the values that they share. So let's do this. Oh, so he has a little help before we do that. Um, he likes to write all the sets that we have. So X, the not X would be the C, D, E, 4, and 5. So if this is Y, this would be the not Y. If this is Z, this would be, or he didn't put the not Z. But okay, so let's go ahead and start with 23. So 23, only the elements that are shared between X and Y. So we have X has a B, um, and Y has a B. X has a 1, so Y has a 1. X has a 3, Y has a 3, and that's it. Those are the only three elements that that are shared between X and Y. So this is the intersection of X and Y. Oh, the next one. The next one is the union of X and Y. So that means all of the values in X, all of the values of Y, without including duplicates. Okay, so we have X has A, B, 1, 2, 3, and the ones that X doesn't have but Y has are D, 5, and only. That's it, right? So that's my union of X and Y. 25, X naught. Oh, he has it already there. We already did it, right? All of the values that are not in X or X prime, right? So X prime is all of these, right? That we already did. C, D, E, 4, and 5. Oh, this one's a little bit more challenging. Says X prime or not the values in X with the intersection of not the values in Y. And that's, I guess that's why he did that extra work, right? So we're gonna look at X prime, which is C, D, E, 4, 5, and Y prime, which is A, C, E, 2, 4. And we only want to look at the values that are in both of these that they share. So the only values that they share are C, E, and 4. That's it, right? Those are the only values that are in both of those primes that are shared between the two. How about 27? X prime intersection with Z. So not the elements in X, but the elements in Z. Oh, see, that's why he didn't do the Z naught, because we're not going to use it. All right, so not the elements in X are C, D, E, 4, and 5. The elements in Z are B, 2, and 3. So I only want to look at the values that are shared in both. So do I have any? So no, there's nothing that Z naught has that Z has. So this is the empty set. I don't put anything. I don't put 0. It's just two brackets with nothing in there. That's the empty set. Or we could use the 0 with a slash, right? All right. Ooh, a little bit more complicated. On this one, we have to do order of operations. Okay. We first have to look at what's inside my parentheses. And then once I have that, then I can do that union. So what's inside my parentheses? I have an intersection. I have Y intersection with Z. What that means is only the values that are shared between Y and Z. Okay. So let's look at only the values that are shared between Y and Z. The only values that are shared between Y and Z are B and 3. That's it. That's my intersection. So now that I have that, now I'm going to do the union of x with that, right? So x union with bn3. So x is a, b, 1, 2, 3. So the union would be just a, b, 1, 2, 3 because we don't include the duplicates, right? So it's just that a, b, 1, 2, 3, right? Hopefully you all see it's clear. Again, please stop me if you have any questions if I'm going too fast. All right. So again, what we've been doing is what's called Venn diagrams. So now let's look at Venn diagram with 3 sets. Okay, it's not challenging. It's just the same concept. Okay, so one of the things that you want to see is that when we're looking at Venn diagrams, for instance here the way we labeled it G is shared by all of the 3 sets, right? So that would be the one that's intersecting with all of them. Okay, so let's look at some examples. This is my universe. Let's say my universe is A, B, C, D, E, F, G. Okay, that would be A, that would be B, that would be C. Okay, and then we can show some of the work. The intersection of A and B, it's very easy to see the answers when we have a Venn diagram in front of us. We only want to look at the letters that are shared between the 2 circles, A and B, and it's easy to see that it's just D and G, right? How about the intersection of A and C? Oh, it's easy to see that the intersections of E and C are just E and G, right? How about the intersections of B and C? Oh, it's easy to see that just the things that overlap are the G and F, right? Or F and G. Um, what else does C have? Oh, a little bit more challenging. A intersection B intersection C. So what do these all 3 intersect? Which is what I was talking about at the beginning. G is the intersection of all 3. It's shared by all of them. Okay. All right. So I think this is the last example, which is great because I have 9 minutes. We have a problem that says 60 people were contracted and responded to a movie survey. The following information was obtained. Okay, and it says 6 people like comedies, dramas, science fiction. 13 people like comedies and dramas. 10 people like comedies and science fiction. 11 people like dramas and science fiction. 26 people like comedies. 21 people like dramas. 25 people like science fiction. And your task is to A, use a Venn diagram to illustrate the survey's results. Awesome. Okay, so let's do A first. Okay, so the first thing that we need to know is our universe, right? Our universe is going to be a rectangle box. Okay, we have 3 things going on. We have 3 sets. We have comedies, dramas, and science fiction. So we're going to have 3 circles, right? So we can label them however we want. Um, so first, we start with our universe. Our universe is everybody that got surveyed. So if I add all of the numbers here, that's going to equal to 60. All right, so let's just um, label these C for comedies. And I'm assuming that D would be for drama, yeah. And science fiction S, maybe. Let's see. Yes, S for science fiction. So we're labeling our set C for comedies, D for dramas, S for science fiction. All right, so let's go ahead and um, start doing. Let's start with our intersection, our middle one. What is shared by all of them, right? So it says here, though it's in red, 6 people like comedies, dramas, and science fiction. 6 people loved all of them. So that goes in the center, right? Um, then we have C intersection D. So here we have 13 people that like comedies and drama. That's what the intersection means. So where would that go? Between C and D, but I already have 6 there. So what is 13 minus 6? 7, right? And 6 plus 7 would give me that 13. So very be careful when we're doing these intersections. If we have a number already, a value in there, um, we wouldn't just write 13 because then we would have more than what is supposed to be in there. So be very careful. All right. How about the second one? Um, 10 people like comedies and science fiction. So that means the intersection of C and S. So again, I already have 6 in there. So to make 10, I just need to write 4 right where they overlap, right? Easy stuff, I hope, I hope. All right, the next one. Um, 11 people like dramas and science fiction. So this is the intersection of D and S. So between D and S, and where are we at? DNS. So in DNS, I already have 6. I need to have 11. So right where that gap is 5, right? So 6 plus 5 is 11. All right. Then the next one, 26 people like comedies. Okay, so I'm looking at my circle with just a C. But in that C, I already have 3 numbers there. I have 4 and 6, which is 10, plus another 7, that's 17. But it says that I have to have 26 people like comedies. So 26 minus 17 is going to give me the 9, right? So the 9 goes right on the C. What about the next one? 21 people like dramas. So dramas is my D, but I already have 6 and 5, which is 11, plus another 7, which is 18. And it's saying that is 21. So 21 minus 18 is going to be 3. And that 3 goes there. Okay. And then the last one, 25 people like science fiction. So I already have 4 and 6 is 10, plus 5 is 15. So I am missing 10 more. So that 10 will go there. So, and what he did too was smart, right? When you're doing these Venn diagrams, you always want to start with the center, with all what they all share, and then you work your way out. Okay. So by us doing this, it'll make us answer the following questions really, really easy because we have our picture now to tell us the answer. So now that we've completed our Venn diagram, or have we? What we want to do is we want to count all of the numbers inside the circles, and that number should equal 60. And if it doesn't, what that means is people that didn't like anything, that they said that they probably don't go to the movies, or they don't like comedies, dramas, or science fictions. They probably like I don't know, sci-fi. What is another genre? Scary movies, right? They or horror. That maybe they answered horror, so it's not any of these. So that would be part of our universe because we did interview 60 people. So the remaining, when we add all the numbers that are inside my circles, that's 44. But we interviewed 60 people. So the remaining 16 people are outside my circles that are part of my universe, right? So x equals 16, that's what that number would be outside. So I got 3 more minutes, so let me go ahead and answer these really quickly. Just by looking at our picture, we can see that 9 people neither like dramas nor science fiction. Um, Here, how many people like dramas and science fiction but not comedies? Okay, just looking at our picture, that would be 3, 5, 10 would give us the 18. And the last one, how many people like none of the movie styles? Oh, that one's easy to see, which would be 16, right? Which is outside those circles. All right, guys, I thank you. Hopefully I helped you guys out. No questions? Any final questions? Let me go ahead and stop sharing so I can see my screen here.
Thank you, Mr. Carrizales. Antonio, do you have any questions for Mr. Carrizales? All right. Well, if not, I would like to take a moment to thank you, Mr. Carrizales, for presenting for us today. And I would like to thank Antonio for joining us today. We hope it was helpful. We hope that you have a wonderful weekend. I know this is just the start of it. But before I let you go, I would like to invite you to, not next week, because next week's Thanksgiving and the college will be closed, but the following week, December 2nd, we'll be having our last TVEs of this semester. So for Happy Math Hour at 11 a.m., we'll be going over final exam reviews for both Math 1314 and Math 1324. And then as well in the afternoon, before you go into finals week, the EPCC Mental Health Committee will be talking about test anxiety and coping with stress. So we hope you'll join us. And like I said, I hope you have happy holidays and a good weekend. Thank you for coming today.